Hello everybody and welcome to CS302 Online. Today we are going to be talking about traversals again. So let us go ahead and begin. So basically last time we talked about three traversals, right? We talked about in-order traversals, we talked about pre-order traversals, and we talked about post-order traversals. We have one more to talk about, that is level order traversals. So first of all, I thought we'd start by doing a review of how to do each of these. So first of all, for any of them, you have to go to the left before you have to go to the right. That's a fact. What really matters again is when you print, right? So for in order, first you go to the left, and then after you go to the left, you go ahead and when you cannot go any further to the left, that's when you decide to visit that node itself. So you print it out. And then from there you go to the right. For the pre-order traversal, first you are going to go ahead and print the node, and then you're going to go to the left child, and then to the right child. For post order, you go to the left child first, as left as you can go. And then once you go, there's no more left to go, you try to go to the right on that same node. And if there's nothing else to go there, or once you go all the way to the right, well actually, technically speaking, you end up going left after that. But anyways, once you go as deep as you can go, then you print. So an example of that would be like, something like this. So if you start out with the root node up here and you're trying to do post order, what you do is you go as left as most as you can, which is here. At that point you can't go any further left, but then you have to try to go right. So you try going right. So when you get to this node, you don't just keep going right. Every time you visit a node, you reset the sort of the where you have to go. And so you then, because there's a left, you keep going left as far as you can go. So when you get here, again, you can keep going left. Then you get here, and then now again, you can't go left. So you try going right. You get to this node, and then you should try to go left first, but you can't. That's when you're like, okay, then I guess I gotta go right. You get here, keep trying to go left, you can. Then you keep going more, but you cannot. You cannot go right either. That's when you say, okay, this is the first node to print out. Okay? So if I was looking at how this would actually print out, then it would be print out this first, and then this, 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 and then from there it actually would be this one, and then this one, and then this one, and then this one, and finally at the end you'd get the root. Okay? Now what if this was pre-order? Well, if this was pre-order, it would look very similar, but almost kind of like a little bit backwards, because with pre-order, the first thing you do is you print. So for that, you would actually just go to pick a different color. So first you would print out the root. So every time when you do pre-order, the first thing you print out is always the root. We'll take advantage of that pretty soon here. And then from there, you try going to the left, you see this, so you print it out. And then you go further, you see this, you print it out. Then you try to go to the left, but you can't. So after that, you give up, you come back to the node, you try going to the right, and this time you can. So you go ahead and you print this. From here, you try again to go to the left. So again, you always try to go to the left first. You go here, you print this, go left further here, try going left anymore, cannot. Then you try going to the right, you can, print this out, try and go into the left, nothing happens. Go back, try going to the right, yes you can, okay, print this out, try going to the left, okay, print this out. Try going to the left, nothing. Try going to the right, nothing. Okay, come back. When you come back, in the case of pre-order, you've already printed, so you just kind of keep going back. You kind of unwind it. So you go back here, go back here, go back here, go back here. In fact, here, let me use arrows. So you keep going up, up until you get here, and then you just went to the left, so now you try going to the right. And by going to the right, you visit this. Nothing here, so you come back here, then come back here, come back, and finally when you're at the root, you're done at that point. Okay? So that's going to be your pre-order. Now for the in order, well, it's kind of messy as it is now, but we shall try. Let's pick a different color. This is blue this time. For the in order, first you gotta go left as far as you can, and then before you go right, that's when you print. So in this case, you go all the way here, but only at this point when you can't go any further left, you come back and then you print this out. So the first node that you actually print out in this case would be this node right here. Okay, that node is the first node that you print. So recursive print functions will be beneficial for keeping track here. Absolutely. Like literally, there's two ways of doing this, the hard way and the easy way. And of course, we all want to do the easy way, and the easy way is to use recursion. Like this is what I tell the 202 people, that when they get to 302s, when they really see the advantage of recursion. This here, Traversals, I would say, is the first real obvious example where you want to do something recursive. I mean, quicksort and merge sort, sure, but like this, like, it's just like, it was born to be recursive, basically. Like, doing it any other way would be just like harder, unnecessarily harder. So that's the next thing we're going to look at, actually, how to actually implement this. But anyways, to finish the in order one, so first you print that one out, and then you go to the next node. Let me actually let me redraw this because too much color. Like I can't draw over these colors anymore. They're like too like dark. So maybe I pick like brown, that would have worked. But okay. From there it is like, I think it's here. It doesn't really matter. It doesn't have to be the same, but kind of wanted to. Okay, here we go. So we have the same thing. By the way, this is not a degenerate tree, but it's very, very close to being one. I'd say it's like almost a degenerate tree. In fact, there's only one node that is preventing it from being like officially a degenerate tree per se, and that is this node right here. If that node was not there, then this would be like fully degenerate tree. So this is like almost a degenerate tree. In fact, I would still almost call it a degenerate tree. Like I would be like, yeah, it's pretty much degenerate, because it's really like -1. So yeah. Now there's no official thing that says like, you know, +/-1 is degenerate. I guess it's just a term like anything else, okay? But official, like pure degenerate tree means there would have to be only one child to each node. So anyways, we start here, and I'm only gonna actually highlight them once I print them, okay? So first I start here, but I go down, but I don't print yet. I go down, and then from here I can't go any further left, so I kind of come back, and then yes, that I print there. So that's the first node that gets printed. From there, now I go to the right, and you know, if I keep trying to go left. So, and again, this is in order, okay? So in this case, I try to go left, I visit this node, I keep going. Okay, I'm here now. I try going further left, but there's nothing at this point. That's when I print this node out. Then I try to go to the right of it. So I get here, try going to the left, but there's nothing. So I print this node. Then I go to the right. This time I try to go to the left, there is something, cool. I get here, can't go to the left, all right, print it out, try to go to the right, there's nothing to the right of that. So at that point, I'm done with this node, so I come back up to whatever was before me, my parent, and then from there, I just came from the left side, so the next thing I do was I print it, and then I try to go to the right, but there's nothing to the right, so I come back up. From here, I just came back from the right side, which means I'm pretty much done, so I just keep going back up. Yet again, I came back from the right side, so I just keep going back up. I go up here. Now in this case, I came back from the left side. So the next thing I do, remember, LPR, in this case, it's print. So I go ahead and print that. Then I try to go to the right, but there's nothing. So I just come back to this node. This time I came back from the right side. So I'm done with the node and I keep going back up. In this case, I just came back from the left side. So the next thing I do is I print it and then I go to the right. So now I come back to this node. I try to go to the right over here. There's nothing. I just came back from the left. Sorry, I said wrong. I try to go to the left. I said I think it right. So I try to go to the left and there's nothing here in this node. So I come back from the left side and then I print it and then I try to go to the right, but there's nothing, so I come back from the right side. Then I come back up from the right side again, there's nothing to do, come back up from the right, there's nothing to do again. Then I come back up, and now I just came back up from the left side. So the next thing I do is I print it, then try to go to the right, but there's nothing there. So I come back again to the node, then go up to the parent, just came from the left side, so I'm going to print, and then try to go to the right, but there's nothing. Okay? If there was another whole part of the tree up here, that's when I would go there, but not before. So finally, I come back from the right side to the root node, and there's nothing above it because it's the root node, so that's how I know that I'm done. Okay? So again, same thing we did last time, but just a quick refresher. But of course, there is one more that I actually forgot to tell you. Well, we ran out of time too, so I'll just say we ran out of time. And that is the level order traversal. So what is the level order traversal? We can actually do it with that example, but I have to draw it yet again. So let me draw that one, but I'll also draw other examples, because that's not quite the best of examples for level order. Again, these circles represent data. I don't really care at this point what that data actually is, but it could be numbers, it could be whatever, like it doesn't matter. Whatever it is what you print essentially. When you call print, you print out whatever the data contains there, okay? I'm sort of separating myself from what is actually contained here and just talking about the data structure itself, okay? Which is a good thing to kind of think about. But if you want to imagine stuff, throw in numbers in there, okay? In fact, for the assignment, you have cars, I think, that you have to throw in because it's a hidden message. So, yeah. Anyways, we'll do this example with level order, but first let me do a more basic example. So let me draw a more traditional tree. There we go. That's a nice tree. I was going to say Christmas tree for some reason, but I don't know where that came from. So anyways, what is level order? Okay. Remember the word level. We were talking about the level when we talk about properties, right? The different levels is kind of like the stages here. And so when we say level order traversal, we're just basically saying to print it out from left to right per level. So what that means is that first you start with a root. So every time you print level order traversal, the first thing you print is the root. From there, you print out from left to right. Again, I guess I don't know if left to right is part of the official level order traversal. Maybe right to left works too. But I guess for us, just so we're on the same page, we'll go from left to right, okay? But what it means is take the next level, which will be this one right here, and print them out in this designated order, where it's left to right or right to left. Again, for us, we'll just say left to right. So that means print that out first, and then this. So the order that these things will get printed would be this goes first, then this second, and then this third. Next, you can look at the next level, which is those 4 nodes. So you print them out in that order. So we got 4, 5, 6, and 7. Next, you look at the next level, which will be this one right here. And then you go ahead and you print those out in that order. So we get 8, 9, 10, 11, 12. So that's pretty easy when you're looking at a tree if I ask you what the level order traversal is. In fact, that's actually, even though I didn't call it by that name, if we backtrack to like 2 days ago, or I think, the last class, we looked, when we were talking about the different types of trees, and I said the complete binary tree, which I said is how you store a heap, and then I gave you that ordering, which is how you store the tree in the array. That's actually the level order traversal, how you're storing that. Because see, we started 0, 1, 2, 3, 4, 5. That's exactly what we're doing right now. So even though I didn't call it by name, that is literally level order traversal. Now, of all the traversals, this is the easiest one for you to, like, if I ask you what it is, you can pretty much tell me right now. In fact, if I just said like pop quiz and just made you take a quiz right now, I'm pretty sure that you'll be able to get this one correct. The other ones, you know, you have to think about them, possible chance of mistakes when you're going back and forth. But this one, I'm pretty sure you get correct as long as it's a good drawing. If it's a bad drawing where, like, I think I also might have an example of that. No, well, that's not a hard one to do. You know, how could you screw this up if there's a bad drawing like this? Like that. And then you accidentally are like, well, this is one level, this is another level, and then this is a level, and then this is a level right here. If you do something like that, where you screwed up this and it wasn't the wrong level because you know the line looks bigger, but technically speaking, the way you should have drawn the levels here is like that, right? It's just kind of because of the drawing itself that this doesn't look right. That's the only time that I could see you screwing up a level order traversal when I ask you. However, it turns out that the level order traversal is the hardest one to implement when you're actually coding. The other traversals with recursion, easy. This one, not so easy, okay? So, yeah, and that's just because you have to do some critical thinking to actually figure out how to implement this. I don't remember, but I think I make you implement it for the assignment. So if I do, then that's the one you want to make sure you save enough time to actually do. Would you still use recursion for this one? Well, there's a lot of ways to do it. You don't have to use recursion. You can use like a stack or a heap. Sorry, heap, no, stack or queue. But essentially, the other nickname for level order is breadth first search. That's why I have up here breadth first. So when you're thinking about the breadth first search algorithm, how you implement that, which we'll talk about in detail later on, is how you'd implement level order traversal. So you don't have to make it necessarily recursive, but sometimes you keep a queue to be able to do it. So yeah, you'll have to figure it out. Like I said, if you totally lost when we talk about breadth first in graphs, that'll directly apply to level order. So that's why I don't remember if I make you do it in the assignment or not. But yeah. Okay, so anyways, going back to this, just to finish this example, I suppose, the next three would be here and then these. So this would be 13, 14, 15, 16, and 17, like that. So making sure you don't screw that up, right? And this will be 1, 2, 3, 4, 5, 6, 7, and 8. Okay? This all looks weird because we're counting from 1, but you know, we're CS people, we don't count from 1, but yeah, okay. So anyways, that's the other traversal. Again, that's called breadth first or level order, depending on what you're reading or whatnot. And that one doesn't have a left print right. It's just print by level, essentially. Print by level. Again, we're going to say left to right in terms of that level. But I think technically speaking, right to left would also be considered like breadth level for level order officially. But just for the assignment or anywhere you see it, the test, for example, please just go left to right, okay? Don't confuse the TA by doing it backwards. So, yeah, I believe I do make you do one more operation in the assignment. I believe I make you do the mirrored traversal. What I think what I just mean by that is just flip the tree. How do you do that? It's actually pretty easy to do. It's just a little trick you'll do with the recursion. I don't want to tell you more about that. Or you can, if you're just totally lost, you can just build a new tree as you go and then just put an if statement. If it's the left child, now becomes the right child, right? You can just keep flipping stuff. But anyways, so let's actually talk a little bit. I don't usually do this, but for this one I want to. Let's talk, because it's a totally new topic, let's talk a little about implementation. So let's talk code for a minute here. And I don't have the IDE open because I think we can just go by hand. Plus I have a lot of the code that I actually wrote in the class last time I taught it. So I can just copy and paste a bunch of it to save time. But let's start with the basics, and that is, how would you actually declare a tree in C++, right? And there's two ways. Again, there's the array way, and then there's a sort of pointer / linked list version. The array way I'm not really going to focus on much because you will do it when you do the heap, you know, with the heap implementation. Which, by the way, I guess I should add it in. Level order traversal is only hard to do if you're storing your tree with pointers. If you store it with an array, then it's extremely easy because all you do is just print the array in order, by the way. Then that is like easy. So I suppose if you're truly lost on how to implement how to implement a level order traversal, just convert your tree into an array version of it and then just print out the array. I guess that could be one way of doing it. But anyways, so we're going to focus on the sort of pointer version of it, which is the more popular one for most of the algorithms, with the exception, again, of the heap being in the array version. But again, the thing about implementing it in an array is it has to be a complete tree, you know, with everything being to the left of it, and all levels being full except for the last one, which is to the left, because otherwise it doesn't work for the basic math. And again, we will focus out when we talk about heaps. But first, just let's do this one, okay? So it'll be very much like a linked list in the fact that you will have a struct called node, or whatever you want, I suppose. Or it could be a class, whatever. I put the word struct, so I don't have to put the word public. But you want your constructor. Well, before we talk about the constructor, let's talk about the member variables. So typically you're going to have three things in here. you're gonna have a left child and a right child. So before, you know, when you're talking about linked list, you had like a next pointer and maybe like a previous pointer if it was a double linked list. It's kind of like a double linked list in that sense that you have two pointers that you have to deal with. So, you know, just call them left and right, I suppose. You can call a left and right child, but that's more writing. So I'm just gonna go with left and right. And then if you do that, then you'll be good to go. Finally, we also want to have the data component of this. I suppose we could make it templated. Why not? I gotta teach templates next week for the 202 people, so this will be good review for myself. So this will be class T. Yep, that's how you do that. And then I would say T data. Hey, let's make it dynamic. Why not? Okay. Ooh. Yeah, okay, that'll work. All right. So now, I mean, this is technically enough, but not, I would say, like, technically, but not really, because the other thing we kind of want to really have here is a constructor and a destructor, especially if it's dynamic. So let's go ahead and make a constructor and destructor. So for the constructor, you know, the same tip I gave you when you were doing linked list is that you want to set the pointers to null if you're not initializing anything, okay? So set them to null. So let's go ahead and do that using the inline stuff because it's cool. So we're gonna say left gets null, comma, right gets, kind of don't like that being split. Let's put that down here. Okay. Now you could make it you could be fancy and make a constructor with default parameters, you know, like make them have node pointers. That way you can, when you create the node, you could already initialize things. You could be fancy like that. In fact, I kind of want to do that just because, you know, for variety's sake. So yeah, so let's do that. So we can say node pointer left and node pointer right, and then you can just basically fill these up. Oh, wait, I forgot the nulls. You do want to set it to null. So let's go ahead and equals null. And then the right one, same thing. Why do I keep putting semicolons? And then no pointer right. Here for this one, I'll do a different variable because otherwise people get confused about this. So I don't want you to think that this is actually initializing the class variable. This is initializing a local parameter. Okay, like that. So technically speaking, here I put either R and then this one left, okay? The fact that they're called left does not mean that I'm initializing the class variable. This is something like the 202 people have to like understand, but I haven't gotten it through past them yet. But you guys will probably understand this because you know this already, right? That when I say node left equals null, I am assigning null to the local parameter of the function, which happens to be a constructor. Then in this line of code right here, that's when I'm actually initializing the class variable with the parameter that is passed in, which happens to have the same name. Now, if this is making you feel a little bit scared, then you can always clarify by using the scope resolution operator with your class name like that. So you know, you clarify that this is actually referring to the name of the class variable, or you can also use a disk pointer like that. Okay? So, but I'm not going to use either because I don't have to. So yes. Okay? So yeah, that's pretty much all the initialization that I have to do, with the exception of the actual data type. The data type, not data type as in one word, but like two. In this case, it's going to be data gets new T, right? And then I suppose because this is a templated function, I have to put, technically I don't think I have to put anything here because I'm putting it inside the class itself. But if I put it outside the class, then I have to put it like a function template. I have to put the word template class T and then blah, blah, blah. So like I have to put the same line here. You know, I have to put it if I was doing it inside of the actual, like here. I think I just don't know how fresh you are with this template stuff. So let me, maybe I'll do that just so you can see. So what I'm saying is, if this happens to be outside of the class, then I have to write the word template here. Class T. The T is, by the way, just an arbitrary name. And then I have to, of course, write the word node, colon, colon, like that, okay? So that's how I have to do it if it was outside the class, okay? But I'm doing it inside the class. And then I would have to have a function prototype here, okay? I think with the function prototype, you would basically put a semicolon here, and then the rest would not be there, okay? But anyways, we're doing it inline because less writing, okay? So this is how we're doing it. So finally, the destructor would be something of the type of delete data. And that's pretty much it. I mean, you can set it to null, dangling pointer to null, but this is a destructor, so this is going out of scope anyways. So yeah, that's pretty much that. Now, this is not good enough code. If you're really coding this for real, then you want to follow the rule of three, right? And the rule of three is basically saying that if you're doing a custom destructor, probably because of dynamic stuff, then you need to overload the assignment operator and the copy constructor as well. Otherwise, you're going to have shallow versus deep copy, and when you call your destructor on a shallow copy, it's going to try to delete the same variable twice, and it will result in a lovely segmentation fault, which may not seg fault in your computer, but on Sally it might, which will make you scratch your head and, of course, you know, panic. But that's probably what's happening. When in doubt, use Valgrind, because that'll give you an error if you're doing a double delete, okay? I mean, you should not have memory leaks anyway, so you're probably running Valgrind already as it is. So anyways, but that's just the basics of how to create a little node for our tree class, okay? So any questions on this? Oh, we do have questions. I didn't see that. That's weird why I didn't see those, but okay. Does the data always have to be a pointer? No, it does not have to be a pointer. I just made it a pointer here to make it cool. But if I didn't make it a pointer, then I would not even need a destructor here. I could have literally just made it like that. But, I mean, from an efficiency standpoint of view, I feel like making it a pointer is better, you know, because the nodes themselves are limited of size, and you can have a bunch of them, versus like, otherwise, they depend upon the size of what you're storing. So I think this gives it more flexibility, but it's by no means required. So yeah, okay. I think those were the questions that I had. I don't know if there's more coming in, but anyways, can you get away with using a singly linked list? Well, you need two pointers because you have two children. So what I mean is, what you can get away is you can start with that code and then modify it. Essentially, you want to start with a double linked list code, because like, I guess the question is, can you get away with making a double linked list with a single linked list? And the thing is, you really can't, because you need a left and the right, and just like you need to prevent them next. Sure, you could do like recursion to print backwards there, but it's not quite the same. So you have to have 2 pointers for left and right. Like otherwise, it just will not work. Like you know, it's like you lost your children. Where are your children? You know, you're gonna panic. So don't lose your children. Have pointers to both of them. Okay. So, what else do I really want to show you? I mean, when you're creating it as the class, like, you know, the class is a pointer. Sure. So if we're doing the class has to be templated now because we made the struct template. So I think we're gonna need the word template here as well. And then when you do that, then and I do believe my solution for the assignment, the James Bond assignment that you guys got, is templated as well. But I don't know if the skeleton code you got is templated. If it is, then deal with it, I guess. But yeah. So this will be class 3. This is not inherit. We're using aggregation. We're not using inheritance. So class 3, and then somewhere in class 3, actually you don't need to make it public. You should probably make it private. Probably a good idea to make it private. Make a pointer, just like in the linked list you have a head pointer. What you have here is your root pointer, which of course is going to be of the type of the node, right? So that's what I'm thinking. Yeah, I think this code will compile with the whole templated magic. Let's see what I had last time around. Did I make it templated last time I showed it? No, these are just the functions. So I guess I don't know. I mean, I still use the left and the right, so whatever, big mystery. But anyways, so it's like a linked list in that sense. You have a head pointer, and you got your bunch of functions like for printing, for inserting, for deleting, etc. So the only one that I really want to focus on is, of course, the traversals, right? So let's go ahead and code one of these traversals. So pick which one you want to see first. You want to see the pre-order one, the in-order one, or the post-order one, not the level order one. So which of those three do you want to see me do? And I'll show you the other two, but I got to start with one of them. So I'm going to drink some water while you guys make up your minds. This will tell me if you guys are alive. Post order it is. Post order was first, so sorry. All right, but we'll do the pre-order after we do the post order. How about that? Okay. So first of all, it's going to be a print function, so we can make it void. So we're still kind of declaring the tree class, so this kind of works out. So in here, we're going to call the function pre-order because I think that's a very meaningful name since this is the pre-order traversal. We don't want to call it the in-order traversal, and then it's like the pre-order traversal. So yeah. And then we're going to imagine, again, I don't want to have to write the word template up here every single time, but we're going to imagine that these nodes are templated or whatever. Okay. So we're going to say, actually, again, it's actually, if it's inside of the class, we don't need to write the word template. Yeah, fair enough. So we'll say, again, this is an inline function, okay? So we need one pointer. That's all we need to start this off. And what do you think that pointer is going to be? It's going to be the root pointer. So it's kind of like, think about when you're recursively printing a linked list, like forward. All you need is a head pointer, right? And what you do is you print the current value, and then you pass in the next pointer to the next item in the linked list, right? And that's how you do your recursion, your base case being that the pointer is now pointing to null. We're basically taking that concept and sort of expanding upon it, okay? So again, we still have the same idea of a base case, that when you finish the linked list, you check whether the next pointer is null. In our case, how we're gonna check if the current pointer is null, that's how we know that we are done. So that's going to be the first thing we do with our base case. We're going to say if cur that was passed in for some reason is null, or because we got to the end of the list, either way, we are done at that point, so just return. Okay? Cool. So, and you guys did say pre-order first. No, you guys said post-order. So you guys are like brainwashed. The first person said post-order, so we're doing post-order. Okay? So in post-order, what do we need to do? We need to go to the left first, then we need to go to the right, and then we need to print last, okay? So this is actually, this will be considered, head or tail recursion? I think it's head recursion. Yeah, it's head recursion. So this is technically head recursion, okay? That says head recursion there. Just imagine it says that, okay? So from there, what we need to do is we need to go to the left child and we need to go to the right child. That is as easy as calling this function on those pointers. So we're gonna say post order. And then here, we're going to pass cur left, right? Because, I mean, remember, cur is a node, and node has a left and a right pointer. So that's all we're doing, cur left, which is kind of like when you pass cur next in the linked list. I don't remember if I made you guys coded recursive linked list when you guys were doing the assignment. If I didn't, then, well, you might want to start off with that if recursion is like really rusty for you guys. But anyways, so this is a recursive call. I'm calling the same function, but I'm not calling it on the same pointer, otherwise I'd go infinite here. I'm calling it on the next pointer, but in this case being one of the child pointers, the left pointer, because I have to go to the left before the right. What am I going to do next? Well, I'm going to copy and paste because I actually wrote that kind of nicely. But in this case, I am not going to go to the left. I am going to go to the right. So that'll be another recursion. Cool, but if I run this code, nothing's going to happen. It's going to run and it's going to finish, but nothing's really going to happen. I still got to do the most important part, which is the printing. But in post order, the printing is the last thing you do, so therefore, I'm going to do it at the end. I'm going to go ahead and say cout, and then I'm going to say cur data. However, I guess because data is a pointer, I got to dereference it, so I'll dereference that in a minute. There we go, dereference. Now, why do I not need parentheses here? Because order of precedence, the arrow operator, or in general, the member access operator, has higher precedence than the dereference operator, which is the asterisk. Therefore, doing this would look amateur because you don't need it. So I'm not going to put it. Okay? So from there, I'm going to go ahead and I guess just maybe I'll put a comma to separate them and a space. And then just to make sure things print out in the right order, I am going to flush. Okay? And maybe at the end when it says null, maybe I'll do two things actually here. I'm going to see out an end line so it looks prettier. Oh, no, because every time it sees null, it's going to be... Yeah, no, never mind. We don't want to do that. Otherwise, we're going to get a bunch of end lines. So, yeah, we'll do that. I guess we'll just kind of... Whoever calls post order, we'll do like an end line afterwards. That way, it takes care of that situation. Yeah, we'll do that. Yeah, okay. And that concludes the function. Come on. There we go. Okay, these are hard. The struggle is real for me to do those curly braces. That's pretty much the function. That is literally, I'm giving you 1/3 of the solution to your assignment potentially. Is flush the same as endline? Yes, pretty much. So endline is like flush plus line feed. So yeah, so like if I do cout endline, that's the same thing as doing cout line feed. Is that the right direction of the line feed? I don't know. It's kind of like it's weird when you're writing versus typing. But yeah, these two are identical. Oh no, flush here. What it does is it flushes the stream out. \n. Okay, thank you, chat. So yeah, but yeah. So basically, it guarantees that the program will halt at that point, print out whatever is currently supposed to print out there, and then or whatever has not been printed yet because it could have actually been delayed, and then continue. This is useful because when you're doing all these recursive calls and things like that, things might start printing out of order and screw up. So you wanna avoid that, even though it will slow your program by flushing or calling end line manually. Okay? So yeah, that's pretty much what that does. You misunderstood, don't pay attention to that. Oh, okay. So yeah, anyways, that's pretty much your post order. So now let's go ahead and do the other ones. Let's do our handy dandy copy pasting for that, because as you'll see in a second, there's a nice little trick that you can do. In fact, I'm gonna copy and paste it like that. I'm gonna change the name here because this is no longer post. We're gonna do pre-order now. So, what do I have to do to change this? Well, first of all, let me just rename everything here since I changed the function name. So this is pre, and this is pre. So right now, this is the same thing. It's actually post order right now. I just copy pasted it, changed the name so the code compiles, but it's still pre-order. Sorry, it's still post order. All I have to do to switch it to pre-order is, well, let's look at how this works. Post order goes by saying left, right, and then to print. However, pre-order is supposed to print before you even go anywhere, and then you go left and right. So notice all I have to do was switch the P to the beginning. Well, all I gotta do here is literally switch my cout statement to before my recursion. So all I'm gonna do is literally swap the order of that. Technically, I just moved the cout up, but what I did is I moved that down so I could move it nicer. But yeah, bam, done. I just did the second third of the assignment basically for you guys. See how easy that is once you understand recursion? That's the beauty of recursion right there. So yeah, and then can anybody guess how I'm gonna do the in order traversal? What do I have to do to that code? So now we got the in order. Yes, copy paste, but what do I have to do now to this code other than renaming these functions again? Move it to the middle, move print before the right. Yes, you guys are indeed correct. All I gotta do is put that cout in the middle of the two recursive calls right there, but I'm gonna, make some space for it. This is where actually copy pasting a computer is faster. There we go. This should be tabbed in. Oh, yeah, we're good. But it actually doesn't need to be tabbed in because it's not part of the assignment. But yeah, there you go. That's it. Be done. They're part of the assignment done, like I said. So it's not hard to do these things. It's actually beautiful. Like the recursion just makes it so easy. So the only hard part here is just make sure you get your base case right. Now, if I remember correctly, I did throw you a little bit of curveball to not, because I gave you basically most of the solution to the assignment. I did throw a tiny curveball in the assignment, and that is that the function takes a pointer, but I can't remember. There's a curve to it, so you have to do one tiny modification to this code to make it to work on the assignment because of what you get passed in, which I think is you initially don't know what the head pointer is. There's something to it. I can't remember, but there's a trick. So while this is pretty much how you would do it every single time, in the assignment, I intentionally added a little bit of a difficulty just so that I can make you do some critical thinking. But that's pretty much it, and that's what I expect in the test. If I ask you, how do we build a tree prior to traversing it? Okay, so that's the second part. So it's a good segue to the next part, which is how to build a tree. So I guess I didn't have to copy and paste any of the code. Now I see why I had so much code written so nicely. It's because I probably did the same thing that I did before, which was literally copy paste in here and temp it. That's how I achieved so much writing of code in so little time. But yeah. Okay, so yes, the next step. How to build a tree. So these traversals are cool, but the whole goal of the traversals is to build the tree in the computer, right? Well, for the assignment, for the first assignment that you guys have, assignment 6, I think it is, the way you build the tree is you read in the input from the level order and build it like that. So that one's easy to do because you're building it from the level order, so it's always going to be the same. So if I tell you use the following level order traversal to build a tree, all you do is you start filling out all the levels completely. Like that, okay? I do believe I use a wildcard for empty spots in the assignment. So like I think it's like X or like lowercase x or a percent sign or something. So suppose that I had something in this format. Then in that case, the tree that you would build for that, assuming that the wildcard meant like an empty spot, actually that's not possible. That's not what I meant to do here. Let me actually do it like this. Okay, there we go. That's more possible. So we start with A, then you go for B, then you go for C, and then you got your two wildcards, which would be like here and here, and then you get D and E. So the final tree is actually that, okay? So I'm supposed maybe we had another one here. Then that would literally go, technically, would go here, right? So when you're building it, you can put those temporarily in there like that, but then just get rid of them, okay? But yeah. So that's how you build it in the assignment. But however, that is actually very space expensive because if I have a tree that is not complete, that's not balanced either technically, but it has a lot of height to it, it's almost like a degenerate tree. If I'm trying to build it with a complete tree, I'm going to require 2 to the n power, n being the number of levels that there are in the tree, right? So like if I had a tree that was like this, and I said build it using the level order traversal, well, the level order for traversal for this would require you to have something here, something here, something here, something here. So you'd have to have 7 spaces to be able to build it, when really you'll only just have 3 nodes. And if I go to another level, so let's say we go to this, maybe 2 more levels, then you're going to need 31 nodes, so 31 characters in your level order to be able to build this tree, right? Of which only you're using 5. So you're using 5, but you need 31. So that's not very space efficient. What I'm going to show you now is how to build a tree using your in order and pre-order traversals, which in this case would be a total of 10 characters, which is still better than 31 by a factor of 3. But this factor increases way more because, as you can see, if I go one more level deep in my degenerate tree, I go from 31 to 63. It's basically another power of 2 added minus 1, right? And so over here, I'm just adding 1. So this is increasing linearly. This is increasing by an exponent of 2, right? So doubling every single time. So as you can see, it's not very practical to do the level order traversals when you're trying to put a tree up. And so that's why in the assignment 6, that's how you do it. But in assignment 7, you do it using the way that I'm about to show you now. Okay? So we still got, we got half an hour, so we should be good to go. So first of all, let me show you why you need 2 traversals, right? I have an example here. Actually, well, my example is literally A, B, C, D, E, so that's kind of funny. I don't know, maybe subliminally I was thinking about that. But let me show you why you need 2 traversals for building a tree. Okay, when it's not the level order with everything being with a complete tree, why you need 2 traversals in like a normal situation. Okay, and so if I said that this is the in order traversal of a tree, and I told you, hey, okay, this is the in order traversal of the tree I want to make. Just go make it, please. Then you could tell me, hey, there's more than one tree that can be made with this traversal. Shall I show you? Let's go ahead and show you. I could have the following tree be, yeah, this would work. And then also have, I mean, I had to question myself for a second there because I have it there drawn and it tells me it works, but you know, don't trust what I wrote some time ago. So yeah, both of these trees, technically speaking, the second one doesn't work. Oh, that's because I wrote it backwards than what I even had in my notes. I should look at my notes. Technically speaking, both of these trees, so this is one tree and that's the other one. So like one is different trees. Both of these trees have the same in order traversal, right? Because when you go with the in order traversal, you go left, print, right. So you go left all the way here. There's nothing here. You come back. Then you print that, there's nothing there, so you go back up, print that, nothing this way, go back up, print that, go this way, go back up, print that, go this way, and so on, and you basically get this traversal here. With this format here, there's nowhere else to go here, so you print this. Nowhere else to go here, so you print this. Nowhere else, it's basically the same thing until you get here, print this, back, and you just go all the way up without printing anything on the way back, and you get this. So both of these trees are completely different, and you still get the same in order traversal. There's one more case, that one I'm going to look here because I don't want to have to think about it, which is this one. AD, why am I turning here? Let's bring this over here like that. Okay, so I think there's actually more cases, but I just have 3 drawn. So this one right here also has the same in order traversal. If we start out, we go left, then we can't go any further left, so we print this A out. Then we go right, nothing left, print the B, nothing right, come back up to the A, then we just came back from the right, so we come back up to the C. We print the C because we just came from the left, so we get ABC now. And then we go to the right, nothing to the left, so you print the D, try to go to the right, nothing to the right of the E, then you print the E, try to the right, sorry, nothing to go to the left, sorry. Print the E, then go to the right, nothing to print to the right, come back up to the D, come back up to the C. So you get your A, B, C, D, E, okay? So now you've seen the totally different trees. All 3 of them are technically different. These 2 look like they're the same tree, but we actually care about left and right. So all 3 are completely different. And so hopefully this shows you that one traversal in order is not enough. Okay, let's try the pre-order one. So what if I told you for the pre-order that the following traversal exists for a tree that I'm thinking in my head? Is that enough? No. Let me show you another example. Remember, with pre-order, you basically print as you go. So that one's actually not that hard to come up with examples. All of this would be pre-order because you basically print. But basically any sort of zigzag that you have would also be pre-order. So like print, and so on. That would also be pre-order there. That one would also be pre-order if I just switch the D to this side at this point. So there's tons of examples for the pre-order. A more fancy one that looks cooler would be something like A, B, C, D, like that. I would also be an example of that pre-order, right? Because you go to the A, you go to the B, come back, go to the C and D. Yeah. Okay? And then post-order. Again, I'm going to give you A, B, C, D again. And yet again, you can come up with multiple cases that have that same post-order traversal. Post-order, remember, you print it on the way back. So if you go all the way deep as you're printing, as you go back up, you print out A, B, C, D. They also have this example here. Well, again, I just flip around, I guess, the zigzagging. So any zigzagging will also kind of screw that up, basically screw it up. But yeah, that's pretty much it. So yeah. The inception assignment was basically an in-order traversal of a tree, right? I think it was pre-order traversal. I'm not sure. Actually, no, it was level order. Wasn't it level order? I don't remember, to be honest with you. I think it would have been pre-order actually, because we started out with like one layer and it goes into another layer and then another layer like that. So I think that was pre-order. I don't know. It's been what, like a year now? It's kind of left my mind at this point. But I'm glad you guys remember that. So, well, actually, no, we did it in December too, right? Yeah. But anyways, so essentially, yes, hopefully this shows you that one traversal is not enough, right? It's not enough to be able to actually figure out what the tree is. Yes, you guys will never forget. Like, burning it. I mean, I coded the thing, so like I had pains too when I was coding it. But you know, once I finished coding it, I'm like, hey, I'm done. So yeah. So anyways, for showing you the next algorithm, I have some like solutions ahead of time because I need to figure out an ordering that will actually build a tree. I can't just pick random letters. So I have, actually I'm going to use the one, I have this one here, or I have that one there. Which one should I do? I'm going to do this one because it's smaller, and then we can do that one next time. Because, yeah, otherwise we're running out of time. So, and I really want to explain the algorithm and then go over it next time. So, the concept here is that we are, instead of using one traversal because we saw that they're not quite enough information in one traversal, we're going to use a combination of two. But it actually turns out that if you have pre-order and post-order, it does not work. You need to one of those two to be the in-order traversal. As long as you have the in-order traversal and then either the pre-order traversal or the post-order traversal, then you're good to go. So in-order plus and then either the pre or the post. You need two of these, one of these and one of these, so two total, to be able to achieve this tree. Okay, we're gonna go with the pre-order traversal, or actually post-order, because this one's using post-order. But I want to show you pre-order. Maybe we'll do the big example then. Okay, I think pre-order is a little bit nicer to think about. So yeah, we'll go with this one. Whatever. So let me go ahead and write the example down. J-I-G-E. So I'm using letters in this example. F-O. And there's one catch to this algorithm. That is, you can't have duplicates. If you have duplicates, the whole thing breaks. So, and there's a reason for that. Actually, it doesn't always break, but there's a high chance that it will. So we'll just say no duplicates, okay? What does that mean? You can't have two letters. Yeah, you can't have in the thing two of the same letters, basically. So what do you do if you have duplicates? Well, you got to be able to identify them. So when you're building these traversals, JRKLP, then you need to do like L1 and L2 or something like that. So I do think I did screw that up on the assignment. So I don't know if I updated it for assignment 7 because I used duplicates. So I'll have to figure that out if I updated that. Because I don't remember I screwed that up. I put duplicates in the input. I'll ask Spencer or one of those guys since they did the assignment. They probably have good solutions for it, so you guys can actually use it to test. Like the assignment is okay, but the sample test I don't think is okay. So yeah. I'll ask them that, or you guys ask them. Somebody ask them. I don't know if I remember. I'll try. But okay, so This algorithm is not hard, but it's hard to explain without doing it. So what I'm going to do is I'm just kind of going to start the algorithm, and then basically you kind of see how it works, okay? And we'll do examples of this again next time too. So yeah, because there's like, I can try to explain it before I do it, but you're just gonna be like confused. Like basically what you do is this. You look at your in-order traversal and you look at your pre-order traversal. And there's one thing that is very useful about the pre-order traversal. And that is that the first node is always the root node, right? Because when you do pre-order, you do print and then you go left and right. So always in the pre-order traversal, the first node is the root node. By the way, where the post-order traversal is just the mirrored version of this. The last node is the root node. So in that one, you actually start at the end. So that's why I wanted to do the pre-order first. Okay? So we know that this is the root node of the tree. Okay? So what you're going to do is essentially you're going to work your way in a loop from the J all the way to the P. Okay? So you're going to work your way through that. But now you got to figure out where to put those letters. Okay? And this is the order that we're going to be inserting them is going to be the order of the pre-order traversal. Okay? So what you need to do is locate, and this is why you cannot duplicate because otherwise you can locate the wrong letter, is you need to locate the root node inside of the in-order traversal. And you keep these in arrays, basically, okay? So it turns out that the root node is right here. Oh, snap. Well, it's not anymore. Now it is. It's right there, okay? So how do I know it's there? Because I literally do string matching and I find the J right there, okay? So I know that the root node is there. I've identified where it's at. This is where it gets a little bit abstract. Let's think about what the other nodes are in relation to the root. For that, let me go ahead and write here my LPR, okay? So I know that I've gone as far left as I could, and I basically looked at the entire tree that is on the left side of the parent, right? So if you consider this to be the root node, these are all the nodes to the left, and these are all the nodes to the right of this node, okay? Whether it's the root node or a child node potentially that's somewhere internally in the tree, an internal node basically. So any node that is on this side here must have appeared in my in-order traversal before I actually print out that root node or that parent node. And any node that is on the right side of the tree must have appeared after my node that is that root. So what that tells me is if I'm looking at this here, this list of letters, these letters right here must have come before the root in the in-order traversal, which means that they must all be to the left side of the root. And all the nodes to the right of it, hold on, different color here. All the nodes to the right of it must be on the right side of that. So if I was to sort of draw my work in progress of this tree, it would basically look like this. Let me copy paste this. Actually, let me copy paste it with the colors. Take that down, get rid of the commas, and put arrows. Even though I don't know what the structure of this tree is yet completely, I can tell you with a guarantee that the nodes that are on pink are on the left side and the nodes on blue are on the right side. Okay? Now, I don't know if internally, like, which of the parent is, who's the parent, who's the grandkid, like all that ordering, I don't know. But I can tell you right now that G, F, E, O, I are on the left side of the subtree. Okay? I'm not going to see on the final result the G on the right side. Okay? Does that make sense? That's the part that, like, it has to make sense before I keep going. Like, that's the part that you just have to kind of visualize. Okay? So let me give you another example. Suppose we have the following tree. C and then maybe like D, F. I don't know. Okay? So if you are doing this traversal here, you know, the in-order traversal, C and A get printed because you go here, and then you go here, and then the B gets printed, and then here you start printing the D first, then the T, and then the F, right? So as you can see, left side, right side. Okay? All right, let's go a little further with this, actually with the same example. Okay, this is left side, and then this is the right side. But also, you know, let me even erase this part so that you can see deeper here. Looking at just this part alone, the same holds. Look at that. T is in the middle of D and F in the traversal. And so the same holds. When I'm looking at T, the stuff to the left of T is literally to the left. And the stuff to the right is literally to the right. So the same holds. And that's actually what we're going to take advantage of to go the next step here. All right, cool. So what we're going to do next is this. Go back to the pre-order traversal, because remember, that's what I said. The way we're going to be done with this algorithm is once we go through each of those letters, J, I, G, E, F, O, R, K, L, P, in that order. So, it's like pivot points in quicksort. I don't know. I've never thought of that comparison, so I don't want to say yes or no, because I don't know if you're thinking it the same, right? So we'll keep going. How about you tell me later on if that's what you were thinking? Okay? So, all right. The next letter that we're going to look at is the next letter in the pre-order traversal, which is I. So what do I have to do next? Okay, what I have to do next is I have to look through the in-order traversal and identify where I is. Okay, in fact, I'm actually going to use a different color for each letter so we don't get confused. All right, there's I. And again, this is why there can be duplicate letters, because then you might pick the wrong letter. Okay, so you find out and you get the I is there. Okay, what does that mean? Okay, so this is even trickier. With a pre-order traversal, you know, you can't visit or print a node until you printed out all of its parents, right? Because with a pre-order traversal, such as this, you know, as you're printing, as you're going through, you print, right? Even if you look at the source code, you know, that I had up here, the first thing you do with the pre-order is you print the node. So it is physically impossible for you to see, as long as you do your end lines, I suppose, or flushing, it is impossible for you to see a child node to be printed before the parent, okay? So when going back here, that means that I must be, if it's printed after the J, it must be a child of J. It could be the left child or the right child, that we don't know, but it cannot be a parent of J. It has to be a child, because otherwise it would have been printed first. What about G? G gets a little bit more different, because G could be a child of I, but it could also be a child of J. Okay, we don't know where, because like it could be technically, if those were the only three letters, they could be like this, but they could also be like this, right? That we don't know. We don't know yet which it is. But what I can tell you is that G is a child or grandchild of J. That I can tell you with a guarantee, because J was the first letter. Okay, but anyways, we're going a little bit far. We're going back to the I. The I has to be a child of J. Now, which child is it, the left or the right? Well, that's the thing. We look to see which category is it at. Is it in the pink one or the blue one? Because it's in the pink one, it means that it must be the left child. It has to be. Otherwise, it would have been under the RKLP. If instead of R, I'd see an I there, okay, then that would be on that side. But it's not. I see it on the pink. So I have found the next root node here, okay? So in this case, I'm going to go ahead and copy and paste this. What this is telling me is that, and also let me copy and paste this right here. How much we have? I think we have enough time. What this is telling me is that I have found my next root node, which is I. Okay, so that is going to become sort of its own sublist. So let us go ahead and ignore this side for now. So let's just delete that for now. And let's focus on this, okay? So we go ahead and we analyze what letters we have. To the left of the I, we have G, F, E, O. And to the right of the I, we technically don't have anything. Between the I and the J, there's nothing. See that right here? There's nothing right there. That means that the I has a left child, but no right child. There's no right child, because if there was a right child, it would have had to be here in between these two letters. Otherwise, no right child. So we can actually use that to our advantage. Because now, I'm going to go ahead and say that I is the parent here. And then to the left of that, I got all of this stuff. And to the right of it, I've got nothing. Okay? So I'm getting there. I'm building my tree slowly. I'm getting there. Okay? And then the other stuff to the right of that still exists, but we didn't write it. Okay? So that's the next step. Cool. All right, moving on. We go to the next letter now. So let's pick brown. G. G is the next letter in the pre-order traversal. G must be a child of either J or I. How do we know? We see whether it's to the left or the right of these letters. Now here's the other advantage of this. Because of the way pre-order works, we're never going to have to worry about working with any of these letters until we finish the entirety of the left side of the tree. So really, I only need to search here in this part, right here. So it turns out that yes, G is indeed right here. Okay? That means that G is a child not of J, but of I. So building on from this, the next step says that it's a child. Now, is it a left or a right child of I? Well, we already determined that all of these letters have to be to the left of it. So, and there's nothing to the right, so it has to be a left child. So that's where G is going to go. Okay, because that's the next letter. And so now, yet again, we have to see where F, E, and O go. Well, it turns out that there's nothing to the left of G, and all three of these letters are to the right of G. That means that over here is going to be F, E, and O. We don't know in what order those go. We just know that they have to go somewhere to the right of G. And that they all have to go again to the left of J because they're on the left, they're before the J. Okay, we keep going. All right, let's look at the E. So E is the next one right there. Okay, so this one's a little bit more interesting because E has something to the left and to the right, right? On the left side, we got the F, and on the right side, we've got the O. So that means that because this is the root node, and this is to the left and that's to the right, that means, let me make my colors match, otherwise you guys will get confused. Because this is the middle, it means that the F is going to go to the left of the E, and the O is going to go to the right of the E. And even though we know, but the computer doesn't know yet, we have just finished doing the left side of the tree. Technically speaking, though, again, the computer doesn't know. So the computer is going to go one more time, and it's going to look at the next letter. So what color have I not used? Dark green. It's going to look at the F. It's going to see the F, and it's going to look to see if there's anything to the left of the E of the F, which we haven't done yet, which there's nothing. And there's nothing to the right of it because, again, the E is already it's already been done, and the G has also already been done. I have a hard time pronouncing these things today. So therefore, nothing gets printed on either side. Similarly with the O, nothing and nothing. So typically, though, you can automatically set left and right this way by when you see the size of the subarray. Kind of like Quixer in this sense. The partitions are of size 1. You don't need to keep going further. If it's only one thing, then that's just a child right there. If there's multiple, then you still got to keep going to figure out where people go. But if there's just one of them, then that's got to be the child. And if there's none, then that means there's no child. Keep it at no. So yeah, that's that side. Cool. We still got 6 minutes. We can finish this. All right. The next letter that we're going to look at. So technically, we already looked at the O here. So colors, we're running out of colors now. What is white? What does that mean? Oh, it's like some weird shade, but let's not do that one. I think we've used this purple shade. Yeah, there we go. Okay, so that one takes care of O. All right, so next we are going to look at one more. Let's use the darkest blue for that. We're looking at, that looks purple to me. We're looking at the R. All right, the R is to the right of the J. So that means we finally are going to start working on the right side. So let me go ahead and redraw that actually. So let me take this and start out on the right side of that. So to the left of it, we got all the tree done for. It's this tree here. But now we're looking at the right side, which has an R. a K, an L, and a P that we don't know how they go. They could go like degenerate style. They could go like nice little, you know, both children each and whatnot, and so on, right? We don't know that. But we're just looking at the R. So because we're looking at the R now, guess what? There's nothing to the to the left of the R, and all these three are to the right of the R. That means that R is indeed just a parent, and it's a single parent, like that. Cool. Moving on then. I think we haven't used this screen. Yeah, we haven't used that green. Cool. All right. So we're looking at that at the green at the K. The K is found here, as you can see. That means that there is nothing to the left of it, and there's two things to the right of it, which means that it has no left child. It's again a single parent. It only has right child, which has an L and a P. We don't know who's who there, but you know, either L is a parent or P is a parent, but they're both technically, you know, what is the word I'm thinking for? They're both technically, inherit? No. Descendants of K. Okay? But we look at the next, oh wait, I think I can do more colors. Yeah. That's weird color. L. So that's going to be the next root. So that means that L is going to be the kid of K. So, and to see where P goes, we see that there is nothing to the left and P's to the right. So that means that P is the right child and not the left child. So it was actually a degenerate tree. It turned out to be degenerate tree on that, degenerate subtree, technically. Okay, so we're done. Now I just gotta put both sides together. So let me do that. Put that one in there, and then bring this one in. And there we go. We have indeed built a tree. Let's see if we have the right answer. Let me scroll down here in my old notes. Yep, that's literally the same thing I have. Well, here. Do I have it here as well? No, I don't. So I can't show it to you. But I'm looking at old notes, and I have the same answer. So either I made the mistake twice, or I was right. So, yeah. Okay, so that's the algorithm. When you're implementing this, there's a couple of tricks that you have to think about, but it's a lot. I suppose I guess you can think of it that way with Quicksort in the terms of like you got to make sure you keep track of the indices, the left and the rights, to make sure you don't screw that up. So you can mark letters as complete and then look to the left and right. You just got to make sure, as you saw there, that you know where things start and end. So you can do that with like a left and right indices, like I guess like Quicksort in that sense, or you can also sort of keep these little vectors that contain the rest of the letters to work with, and you can just keep passing those as you're doing the recursion until they become empty. So there's a lot of different ways that you can do it, but you have to do it, I guess. So that's basically the assignment 7. So I guess 6 and 7 are due in 2 weeks from now because they're basically the same assignment, but you know, first we make you do the traversals, and then we make you do the actual building of the tree using traversals, because you kind of have to know traversals to do the other part, but they're the same thing, like the same concept and everything. So we'll do a lot more examples on this. We'll dedicate most of the next class to do examples, and then maybe I also want to talk about some other cool things with trees, like useful usages of it, like binary search trees and things like that. So that'll be next class, along with examples of this, and then from there we'll jump into AVL trees. So that'll be historically what people have the hardest time with. So students have the hardest time with. And that one, you go back to the Star Wars themes for the making an AVL tree. Which method is preferred, pre or post order? So it doesn't really matter. I mean, you haven't seen an example of post order, but like if we were doing the post, do I have a post order traversal of this one? I mean, we can make it on the fly, but pretty much you'll see that it's basically the same thing but backwards. You start up from the end and you work your way to the left, and then you'll see it. So like, let me have a minute. Let me try to do the post order for this. So post order for this is going to be left and then go right. So it would be F O E G I P L K R J. Okay, so that is the, let me make this all smaller so it fits in one line. That's the post order traversal. And so if we look at this, the in order traversal was GFEOIJRKLP. And so as you're building this, you would notice immediately that this is the root node, so you start at there, and the next thing you do is the R, so that must be the descendant of this as well. So the R is to the right, so you put it here, and then that takes care of that. The next thing you do is the K, so the K is to the right of that, and then from there you do the L, which is to the right of the K, and then the P, which is to the right of the P, so you do that side. Obviously I'm going really fast here. I just want to show you a point that it works the same way. So that takes care of that and that. Then you look at the I, which is to the left of the J, so it must be here. And then you look at the G, which is to the left of the I, so it must be to the left of it. And then you look at the E, which is to the right of the G, so it must be here. And then the F is to the left. Sorry, the O is to the right, and then the F is to the left. So as you can see, let me make this G nicer. You basically get the same thing. And all you're doing is you're working from the other end. So it really, like, if you're coding both methods and like in your computer, it's a matter of just basically flipping your loop, like from like for int I is equal to 0 to I is less than size or whatever, to like for int is equal to size minus 1, I is greater than 0 or greater than or equal to 0. That's pretty much it. So it's very easy, okay? So yeah. Again, I'll go more in detail with these examples, but yeah, it's there's literally very little preference. I guess from a visual point of view, the pre-order looks nicer, you know, because you're starting from left to right. Like we Westerners like to write, you know, this way. But maybe for people that write from right, did I say right to left or left to right? I don't know. You get the point, right? We write this way, and so solving problems this way is easier for our brains versus like the other way because we're not used to that. So I guess that's just the thing. I'm left-handed, so like I have a hard time with the whole left and right. So and it doesn't help that the camera is not mirrored. So like when I'm saying something like this, I'm actually going left to right, but you see it right to left because of the camera thing. I would have to mirror my image to make it match like if I was doing that. So the struggle is real. You know, online learning. But yeah. Okay, that's pretty much what I wanted to cover today. So I'm actually glad we got to what I needed to. That way you have a solid amount of time to get going on this. And then we will reinforce this on Monday. Do we have to make a recursion relation for every assignment? For every part of the assignment that involves something that can be made a recurrent relation of. So something with recursion. So like, yeah, these are the perfect examples of recurrent. By the way, what would the recurrent relation of this? It would be linear time for any of these traversals. For building the tree, that's different. But for doing the traversals, it's linear time recursion. So I actually have a thing on that I'll talk about next time. But yes. When you're doing your write-up and you're doing the big O analysis, you want to show how you derive that with the recurrence relation because A, we spent a lot of time working on that for like the first 3 weeks. And 2, it's good practice on like real world applications of recurrence relations. So yes, please do it. I think that's why the TA was insisting on it as well. Does it say that on the syllabus? No, but it's part of like what it says on the write-ups on each assignment. So just follow along with the write-ups. And as part of explaining asymptotic complexity, always do your recurrence relations. And when in doubt, you can always just send a message to the TA. So, anyways, any other questions or anything before we go? Okay, cool. All right then. Well, since I won't see you until next week, have a good weekend. Stay safe. Hope you guys understood this, but if not, we'll go over more examples next time. So, yes. Or talk to the TAs. They have office hours and everything. So, all right then. Or message me as well. So I real Discord right after. I have to do some stuff, but in the evening I can talk to you. So yes. All right then. I will see you guys later. Stay safe. See ya.